Good afternoon, CS109. How are you guys doing today? Fantastic. That's what I like to hear. We have a wonderful, wonderful class ahead of us. We're going to learn a very critical idea. Once again, we're going to be learning about continuous random variables. This is CS109. Before I jump into things, this is a random photo of my baby, but I was just like heart melted and I just thought I would share, which is really not the important thing. Though, maybe the important thing is it's a Friday, so I like to start Fridays with just a nice story from life. And the story I was going to tell you is actually not related to this photo. Though I guess the short story is like, my day starts normally at 6 again. This morning it started at 5:45 a.m. I feed the baby, I dance party with the baby. It's just like she calls it Yoda, but she means yoga. And we're going to do our stretches. It's a fun way to start. I recommend it. Anyways, but the story I was going to tell you guys today was actually an interesting story from my own life. You guys may or may not know this, but I'm legally blind in one eye. And the story behind that is quite interesting. When I was 11 years old, I was living in Kenya at the time, and I believe I was with my parents, and they were pointing something out, and I was like, should I look out of my good eye or my bad eye? And my parents what? You're not supposed to have a good eye in your bad eye. I thought everyone had one. And so I was like, yeah, I can't see on my left eye. And they're like, we should actually probably look into that. And long story short, something happened to my left eye. It was a disease and not contagious, don't worry. But the thing that happened to my left eye was going to happen to my right eye. And eventually a doctor in Nairobi figured out exactly what it was, and they figured out how to get me the solution. It was a little late for my left eye, though, because it had been bad for a long time. But then at one point, my right eye went as well. But because this doctor had figured out what had gone wrong, they gave me the solution, which is an injection into the eye, which is not the most fun thing, but I get to see because of it. He was able to give me that solution exactly when I needed it, so I was able to keep vision in my right eye, and I can see just 20/20 out of my right eye. And on some level, and the left eye continues to be a pain because it spent so long without being treated. It just causes it's my problem child eye. And despite the fact that this has been something I've had to deal with my entire life, and of course it'd probably be more fun to see out of both eyes, and there's always the risk that I will go blind, it has been the most wonderful silver lining in my life, and I don't know how to express it, but I'm going to try. There is something about being a middle schooler where it's hard to appreciate life. Middle school is hard. But I had this weird experience at middle school where I was like, whoa, I'm supposed to not be able to have one of these primary senses, and yet I do. And so I had this appreciation that was a big part of my life when, there's a lot about middle school not to appreciate. And then there's other silver linings that have come from it. I certainly feel like I relate to a lot of things much better. And a really small silver lining is I came to Stanford. And of course, there's doctors helping me to make sure it doesn't happen to my right eye and to keep track of the left eye. And there's this time when this doctor is about to do surgery on my eye. He's doing a pre-op. He's talking. He's like, oh, what'd you do? I'm like, oh, I was a PhD student at the time, so I'm a PhD student. He's like, oh, what'd you study? I'm like, I study artificial intelligence. He's like, tell me more. And then, of course, because of Stanford, we started a collaboration. We've written 3 scientific papers together. We just have a good time. We nerd out about eyes and probability. And it's just been the most fun Stanford experience. So this really strange disease I have has somehow been a nice little light in my life. And I think one day my vision might just go, and I still believe when that happens, I'll still feel like, okay, that's the cards I've dealt, and it's been such a blessing in such a lot of different ways. So anyways, that's my Friday story. Fruit of the random tree, as my friend would call it, and that's the only connection I have to CS109. Okay, so I have a hook for you guys today. This is an extension of a problem we thought about on Wednesday. So on Wednesday, we learned about the Poisson distribution, and we can ask ourselves, what's the probability of certain numbers of earthquakes within a year? But there's a different spin on that problem, which is probably more relevant to us. We want to know what's the probability at Stanford of an earthquake within the next 4 years. And as that slight different spin will lead to a different answer. It's going to force us to understand continuous probabilities over continuous space. Okay. Quick question. Does anyone know what this is a photo of? Yeah, it's Stanford, and there's Mem2, but it's got this weird tower, and this is from the front of the quad, and it's got this strange shape to it, and that's what Stanford looked like before 1906 when there was a magnitude 7 point earthquake which took down this tower and took down this gate at the beginning of Stanford. Okay, well, we're going to want to be able to answer questions like that, but of course we're going to have to learn some new things to get there. So let's learn some new things, and it's going to build on some old concepts we've had. Certainly we're in this part of CS109 where one of the core things for you to learn is this idea of random variables. And the first random variable we learned was the binomial random variable. It's a metaphor that comes from coin flips. Imagine you have n independent coin flips. Every coin flip has the same probability of being heads. The random variable is going to represent the number of heads you got. In the more general story, it's the number of successes within n independent trials. Such a useful thing that we've called it the binomial random variable. As soon as you define something to be binomial random variable, you inherit a probability mass function, expectation variance. We've gotten very good at this. It also has like the little sister, the Bernoulli random variable, which is like a binomial with just one coin flip. More useful for proofs later on. Then on Wednesday, we bumped it up a notch. We said, let's learn a new random variable. We learned one of the most beautiful, interesting natural random variables, the Poisson random variable, which says if you think about a fixed amount of time, what's the probability of getting exactly k requests? And the magical story from Wednesday, and if you missed Wednesday class, that's an incredible one to go check out. It's that if you just give me an average number of requests per minute, because of the Poisson process and all the things that we can derive with mathematics, we can know the full probability mass function for the number of events within one fixed time frame. That's so much that you get from so little. If you just tell me a rate, you immediately inherit this beautiful graph. And all of this is on the course website. We have all these random variables that we've learned about. Today's goal, though, is to change your understanding of random variables from I'm going to derive them one at a time to, let's say somebody tells me about a new random variable, can I learn it quickly? And can I incorporate many random variables into my vocabulary? So today we're going to learn not one random variable, not two random variables, but we're going to learn 1, 2, 3, 4 random variables in one day. The learning goal really is then, how can you learn a new random variable? One of the points of random variables is you don't have to rederive all the math to use it. If somebody says this is a random variable, you get to inherit all the math that they've done. And I want you guys to be able to work with random variables that you haven't derived. And let me give you a very real situation from your future. Future you has gone deeper into computer science. You are learning more. You are thriving, having a great time, and learning about servers. Well, a big thing for servers is how long a request has to wait in a waiting area before it gets served. And if you learn about it, one of the most popular algorithms is this MD1 queue. And in the MD1 queue, if you learn about it, they talk about how long a request is going to be in the queue, and they talk about it as being distributed as a Borel with parameter mu and 0.2. At this point, you're like, I took 109 and they never taught me the Borel. Hopefully what we teach you at this point isn't every single distribution, but rather how to learn new distributions quickly. So if you looked up the Borel distribution on Wikipedia, it would give you all this information. And from this information, it would give you all the most critical things. And after 109, I want you to be able to read this Wikipedia page and know exactly what you need to be able to follow along the conversation about the MD1 algorithm. What you really need to know is the story, what leads to it. That's the equivalent of a binomial is n coin flips. So a Borel has a story. You should understand that. And then you want to understand these equations too, a probability mass function. That's the relationship between the values the Borel could take on and its probability. You want to know the mean and the variance. And Wikipedia gives all those to you. You might want to go derive them yourself, but more likely than not, you just want to understand this algorithm, and you might be using these equations without derivation. So does that sound good? There is a learning goal for you guys. Future you is going to be so appreciative that you worked on this learning goal today. Okay. Sound fun? Everyone's curious about servers now, aren't they? Okay, good times. So this is our goal for today. We're going to flesh out all of these random variables. You already know a Bernoulli and a binomial, but I'm now going to teach you, or in a Poisson, but I'm not going to teach you a geometric and a negative binomial, and then we're going to learn an exponential. Ready for it? We're going to do two quickly, and your goal is to incorporate them into your vocabulary random variables so that we can start to solve problems. Okay, geometric random variable. If I could give you a metaphor, imagine a Pokeball. If you don't know what a Pokeball is, it's unrelated to the food. It's like this little thing that you throw and you catch a Pokemon. And you throw it, and you might catch a Pokemon or you might not. So you might have to throw a whole bunch of Pokeballs before you catch a Pokemon. If that's not working for you, then how about this? A geometric random variable is one that's distributed as a geo with probability p. And here's the narrative. It's the number of independent trials until your first success. P is going to be the probability of success on every single try. So the one way of reading this is coin flips. It's like a binomial says you have n coin flips. How many heads did you get? A geometric says how many times did you have to flip that coin until you got your first heads? It solves a slightly different problem, though related. So you might say, like, how many server requests do I have to send before one lands? Or how many Pokeballs do I have to throw before I get a Pokemon? It can take on the values 1, 2, 3, up to infinity. Has to be discrete because you can't flip a coin 2.5 times. And why can't it be 0? A lot of our other random variables could be 0. What's wrong with making this one 0?
It can't happen if you do it 0 times.
How are you going to get a heads if you flip the coin 0 times? Come on, not going to work. So very good point. Can't be 0. I am going to point out this pro tip. If you're learning a new random variable, thinking about the values it can take on is such a grounding way to get yourself oriented. And think about why can't it take on 2.5? Why can't it take on 0? So as soon as you buy this story, you could then go and derive it. This is one you definitely could have derived yourself. What's the probability that it takes you n coin flips to get a head? Well, that means you got n minus 1 tails followed by a head. You could have derived this probability mass function. It would have been a little bit more annoying, though, to derive expectation and variance. Maybe expectation's not so bad, but variance certainly would have been quite a lot of work if you wanted to derive it from scratch. So I'm giving you a brand new random variable, and anytime you feel that you can match this narrative, you have these 3 tools you can work with. Does that sound good? Because I'm not going to stop there. I wrote it down over here so you can follow along. I'm going to introduce you to one more before we start solving problems. You're like, I don't care about catching one Pokemon, I want to catch them all. So the negative binomial, that's awful. It's how many independent trials, not until one success, but until R successes. So it's like, how many times do you have to flip a coin until you get R heads? And there's some problems that really nicely fit this narrative. Again, we're going to have the coin metaphor where P is the probability of success on each trial. They're all independent. Every trial has the same probability P of giving you a heads. In this case, what's the probability that x equals n? Well, if you say like 5 here, you're saying what's the probability it took 5 coin flips in order to get R successes? Hopefully R is something like 3, less than 5. Well, you have all these different places where you could put your successes. You have the probability of success, the probability of failure. And you could go and think about deriving this, but the point of today's class is to be able to use something that someone else has derived for you. So as soon as somebody gives you a random variable, you have the valid numbers it can take on. You have the probability mass function. That's the relationship between assignments and probabilities. And you get expectation and variance. Okay, now, do you have to memorize all these? No. CS109's midterm and final will be open book. Anytime in the future when you need to go reference these, they will be somewhere. And for actually, one of the places that you can find them, if you go to the course reader, I made this section called Random Variable Reference. And you can just go see each of your favorite random variables, and you can be like, oh, hey, that negative binomial, here's what it looks like. You can put in different values for R. You can put in different values for P. You can see the probability mass function, expectation, variance. You don't have to memorize them. You need to know conceptually what all these things are. You have to know what PMF is, expectation, and variance, and you need to know how to match the real world to the stories that it tells. Does that sound good? Yes?
Can you just describe again why the negative binomial is different than a regular binomial?
So there, yes, let me try and tell you the story and talk about how they're different. In a binomial, you declare ahead of time how many times you'll flip a coin. You say, I'm going to flip it 10 times, and I care about how many heads. It's a different situation from the negative binomial. The negative binomial says, you're not going to just do 10. You're going to keep going, and you'll keep going until you get R. This number counts number of successes. This counts trials until successes. So they're both talking about coins. They're just counting different numbers. They're representing different values based on those coins. Yes?
Why is it called the negative binomial?
Oh, that is such a good question. I think it has to do with the probability mass function because it has a binomial coefficient in it. But let me double check. I'm pretty sure that's it, but I haven't checked that. I think I asked that question myself like 10 years ago, and I can't be positive that's exactly it. Would you mind double checking and let us know if I got it wrong? Cheers. Okay, question.
What is exactly the probability that we're calculating? The probability of like success?
So in this case, you tell me the probability of heads. So the parameters are what you tell me, and what I'm calculating are these things. So you tell me what's the chance of getting ahead, and I tell you what's the chance of a certain number of trials until R successes. So this probability mass function, if you see probability, let's say x is a negative binomial, x equals 3. That's a probability question. It's asking, what's the chance that the trials until R successes takes on the value 3? Good question. And it's assuming that x was defined, and when you defined x's, you had to say two things. You had to say, how many successes are you looking for? So I'm looking for, say, like 2 successes. That's R. And you have to say the probability of success on every single trial. If it's a coin, maybe it's 1/2. Yes?
Is there a deep reason why the expectation and variance of the negative binomial are exactly R times the expectation and variance of the geometric random variable?
There is a deep reason. We're going to get into the derivation at some point, but just to give you a little bit of a hint. If x is a geometric, well, let's say xi is a geometric, you can think of y, which is a negative binomial. You can say y is the sum of xi's. So it's like time until your first success plus time until your next success, so it's a sum of random variables. And because it has this property, lots of parallels will show up. But if you didn't follow along on that, not that important, but it would be helpful if you want to do derivation. More questions. I love these questions. This is great. Yes?
Sorry, so the value of R here takes a maximum value of n, right?
Yeah, it's kind of flipped a little bit. I would say n takes on a maximum value of R, because R is how many successes you're looking for. Oh, wait, sorry. No, n must be larger than R. Sorry. R is how many successes you're looking for. N is your number of trials. Number of trials must be greater than number of successes.
Be greater or greater than equal to?
It could be greater than equal to. Like if you're looking for, let's say R is 3. I'm saying how many trials until 3 successes? N is how many trials I ran. And it could be 3. It could be 3. You're just like success, 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 drop mic, I'm out of here. Totally possible. Okay. Now the interesting thing here is I'm going to give you some problems. They're going to be using some combination of binomial, Poisson, geometric, negative binomial. And I want you to see if you can find the story that you think matches, if that's interesting to you. Okay, and certainly I want you to know that you can visualize these, you can use these equations. A little gift from the TA team to you. Okay, let's start with dating at Stanford. Each person you date has a 0.2 probability of being someone you spend your life with. Wow, wonderful, I made that number up. What is the average number of people one will date? And then what's the standard deviation? And of course, recall that the meta goal here is to think about what steps would you take to answer a question like this? Practicing the art form of taking a question, finding the random variables, and then using the proper equations associated with those random variables. So talk about it with the person next to you. You have a 0.0000001 probability of that person being the person you spent. No, I'm just joking. Just talk about it with the person next to you. Okay. Now you might be at the point where you're plugging in equations, and if you've gotten to that point, you win, right? Just basically, you could use, there's all those equations I've written are in Python. You could just plug it into a calculator. The goal is, can you get to the point where you know the equation that you're supposed to be using? As I said, almost always we're going to be defining random variables when we see new problems, and this time I helped us out. I'm going to say there was a pretty clear random variable in this question, which is the number of people that you're going to date until you find the one. So that's the random variable I define. But the next step should often be, tell me about that random variable. It may be one we've never seen before, and you have to derive the probability mass function from scratch. But ideally, you can declare that it fits one of these narratives. Did somebody find a narrative that they thought fit nicely?
Well, we want to find the number of people you date until you spend of your life with them.
Yeah.
So we define spending the rest of your life with them as the success, and this can be modeled as a geometric random variable.
Okay, I very much agree. What's the probability of success on every trial? You must give that to define a geometric.
0.2.
Okay. It's number of coin flips until you get your first head, and we're just going to say you have a probability 0.2 of getting heads on every coin flip. Now, as soon as you've done this, then you can answer these questions. What's the average number of people one will date? What's that question asking? It's saying, what's the expectation of x? And at this point, you know it's a geometric, and you can just look up the expectation of a geometric. An expectation of geometric is just going to be 1 over p. So it's going to be 1 divided by 0.2, 5. Fantastic. So 1 divided by 0.2. And then the next question is, what's the standard deviation? So like, what's the square roots of the variance of x? And then again, we can say, what is the variance of a geometric random variable? It's 1 minus p divided by p squared. And the standard deviation is just going to be the square root of that variance. So did you have to derive that this is the equation for people that you date? No, you just recognize that this is another instance of the story we've already learned. So fantastic. The learning goal is really this, then define the question, and then you'll be able to look up your equations. Let's take this for a spin. Okay, another one that's worth thinking about. This is actually an interesting one. It was sent to me by a student who once took CS109. Justice Breyer, who is a Stanford alum, was on the Supreme Court, and they had this question about whether or not a jury selection was biased and how people chose the jury selection. And particularly, they were thinking about whether or not a minority group was represented enough on a jury. So somebody was saying this jury was selected unfairly because it was completely white. And so that was what they were discussing. And it was coming from a particular community where they knew the demographics of the community. Justice Breyer hypothesized a scenario involving, 1,000 balls, 60 are blue, and 940 are purple. So that imagines the demographics from which people were selecting a jury. If you select 12 from this urn, what is the probability of getting all of them being one particular color? Justice Breyer then says something like, you would expect something like 1/3 to 1/2 of all juries to have at least one minority person on them. And then he said, looking at this particular region and looking at the history of juries, they've been clearly choosing them in a biased way. Interesting, Supreme Court involves a Stanford alumni, and it involves some probability. So I suppose my question for you guys is, sorry, he says something. He invokes the binomial theorem. He says, in his defense, he actually said this can be represented as a binomial random variable. So can we do that? Can we represent the number of people on a jury who are coming from the minority population as being a binomial random variable? So let's say x equals number of people from minority. And he's claiming that, or this is y is distributed as a binomial. In a binomial, number of people on a jury. In a binomial, you have to give an n and you have to give a p. In this situation set up in front of you, can you guys figure out what n is and what p is? I'm just going to give you guys a hot minute to think about this. Think about it for a second, and then we'll think about it together. Okay. Hopefully thinking about this, you understand that he's talking about the number of people on the jury. So it's like you have 12 coin flips. And he's saying every coin flip, you have a certain probability of choosing somebody who's not from the white majority in this particular region. So what's the probability here of getting somebody who, I guess he has this story of 1,060 are from a minority. So the probability of any one person being chosen who is a minority is 60 over 1,000. You can then ask the question, what is the probability that y equals 0? And I believe I wrote this up. I love writing things up. It's so fun when we get to do that. Oh, my computer's being slow today. Not scrolling. Wow, we're already onto machine learning. That's exciting. Jury selection. Okay. So I'm going to simulate this. We're going to flip 12 coins. And what's the probability that they all come back purple is the question that he's posing in his Supreme Court. Guess it's possible to come back all purple, but it's certainly not that likely. So this was the defense's argument. It just happened by chance. We were choosing all these juries, and they just always came back all white. But then you can look at the distribution of their juries, and it doesn't fit the distribution it should have been. Now, this is the answer that Justice Breyer talked about. It's a binomial. There's 12 coin flips. Every coin flip has a 60 over 1,000 chance of coming up as, in his metaphor, a blue coin. And he says, what's the probability of x being greater than 1? And you can solve that as 1 minus the probability that x is 0. And we can just use the probability of PMF. And it says about 52% of juries should have at least one person who isn't from the majority class. Now, if you just look at 2 juries, it'd be really hard to talk about bias. But they looked at all the juries in history, and they said it's way, way, way less than 50%. OK, there you go. There's a jury that's not all white. And you imagine about 52% of juries would look like this. So very interesting that he referred to the binomial distribution. He was wrong with his probability. He said a third to a half, but really it should be over 50%, which went, they got some bad math in a Supreme Court decision. Whew, kills me. OK. Yes, question? I'm so glad you asked that. OK, I'm going to just pause and talk about that for a second. The binomial distribution here is not a perfect story. Because in the binomial distribution, every time you flip a coin, you have exactly the same probability of getting heads. And this isn't quite the case, because after you've flipped a coin here, you now only have 999 people to choose from. This probability will change. Not very much, because when that denominator becomes 999, it won't be that different. But it will change over time, which breaks the assumption of the binomial. So the binomial distribution is wrong. But if you guys were curious, one thing that we don't go deep into in CS109 is there's this other random variable called a hypergeometric. And a hypergeometric allows for exactly this sort of change in probability, where every time you pull a ball out of an urn, your probability of pulling that color decreases slightly. If you were really curious to learn about hypergeometric, you would make my day. And then you could go learn about a hypergeometric, put in all the parameters from this problem. You could get the hypergeometric probability mass function, and look at the answer you get. Using the correct random variable, you get 0.5261. And using the binomial, which is a slightly wrong assumption, you get 0.5241. What's the takeaway from you guys there? Binomial does assume probability stay constant. So you were right in recognizing that this was violating it. The next takeaway is if you violate that assumption just slightly, you're going to do just fine. And then the third one, that the world is filled to the brim with wonderful random variables. And someone in this class may discover their own. Because maybe you'll be doing some research or starting a company and something interesting will come up and you're like, no one's ever talked about this particular random variable. And then you'll have your own. And you can name it after me. No, I'm just joking. You don't get to name it after yourself. Someone has to do that. So like you wouldn't call it like, I don't know, maybe discovers one. He wouldn't call it distribution. Someone else is like, not that important.
Why is it called the hypergeometric random variable?
Because what is its related? It's not that related to the geometric, right? It seems like a hyperbinomial would have been a much, much, much better name. And that I'm curious about too. And we're going to check us out and tell us why is it called the hypergeometric. It's nothing to do with the geometric. Hypergeometric looks a lot like a binomial and basically nothing like a geometric. So these people should just name it after themselves. So OK, long story short, you can declare a random variable. If you declared a binomial random variable with these particular parameters, you wouldn't just know the probability of getting a jury with 0 people, you would know the whole distribution. Say, here's the probability of 0, here's probably getting 1 person, probably getting 2 people, probably getting 3 people. You can certainly look at all the juries that have 0 people and say that something's wrong, but you could also use all this extra information that you have to go deeper if you're interested. Okay, we got the demo. I'm going to keep throwing problems at you so we can practice taking the real world and finding the random variables. My next one comes from Bitcoin mining. If you guys haven't heard of Bitcoin mining, I do not know where you've been living. But maybe you don't know the algorithm for Bitcoin mining. The way the Bitcoin mining works is they're going to give you this hashing algorithm called SHA-256. And they're giving you a chunk of data. And then you get to choose a bit string. And when you put these two things through SHA-256, it should give you a number back. SHA-256 is going to give you a number back that you should interpret as basically random zeros and ones. But you win. You mine a Bitcoin. You get, I don't know what that's worth, $20,000 now? I think you get like $20,000 if, for a particular challenge, you're able to produce a salt that leads to a random-looking series of bits that start with G zeros. So if G was 1, you can imagine like every time you try a number, you'd have a 50% chance of mining a Bitcoin. But if G is larger, you'll have a smaller probability. And we're just going to think about that a little bit. You might be able to solve some of these problems just straight, but I do want to challenge you to think a little bit about random variables. But sometimes you don't need a particular random variable. Sometimes you can just solve it straight. Real problem from a midterm, in case you're curious. OK, the first one. What's the probability that the first thing you try will produce a bit string which starts with G zeros? So it's basically asking, if you generate random zeros and ones, what's the chance that your random zeros and ones start with G zeros? Lots of ways approaching this one. Certainly you could do this one without a random variable, but just to show you what looking at the world is like through random variables, let's give it a shot. In fact, I'm not going to push you too much to think about this one because I think a lot of you guys can just look at this and say, the probability is 1/2 to the power of G. The chance that you produce a random bit string that starts with G zeros is the chance that you get a 0 followed by a 0 followed by a 0. Since each one's independent, you can just imagine multiplying those probabilities. But I did want to show you guys being super formal and defining this in terms of random variables. So I'm going to say x is my number of zeros in the first G bits. And in my world, now every bit is a coin flip. It could be a 1, it could be a 0. X is going to be the number of zeros in the first G bits, and therefore, because it's the number of heads in G coin flips, it's going to be a binomial, where n is going to be equal to G. So the number of experiments is given to us as this number G. And the probability of getting a 0 on every experiment is 0.5. And then this question is just asking, what's the probability that the number of zeros in the first G bits is equal to 0? And I can just use the binomial probability mass function, which leads to this thing that people could have derived without a random variable. OK, just a little bit of warm-up. How about this one? This was one where it'd be super hard if you didn't know about random variables. I'm going to give you guys a moment to think about it. What's the probability that you'll need under 100 attempts to mine 2 Bitcoins? This answer we're going to call probability A. That's the probability of mining 1 Bitcoin on any attempt. So it's like a slot machine. Every time you pull the slot machine, this is the probability of you winning. My question is, what's the probability that you'll need less than 100 pulls to get 2 Bitcoins? Questions about what I'm asking.
Wait, is it 0 and is more right there?
Every bit is going to be a 0 or 1, and you get a Bitcoin only if the first G bits are all zeros.
Well, why can't you just like enter 0?
Oh, because you don't get to make the bit stream. You get to like basically pull the SHA-256 lever, and it's going to give you back a bit stream.
And to make sure, the x equals 0 refers to the fact that we want 0 ones to appear.
Oh, did I get this wrong? Should x have been equal to 0? Oh, man, I was just like, I made this example. I brought it into slides today, and that should have said the probability that x equals g. Because if g is the number of zeros, you want to have g zeros. Oh, man, and then I have to do all my math again. But guess what? This is now going to be g choose g, and it's going to be 1/2 to the power of g times 1/2 to the power of 0. This only works out if g choose g is equal to 1. But guess what? If you have g items, and I say choose g items, how many ways can you do that? Yeah, good times. OK, so that does that. at 1. That was a great question. That was a typo on the slides. This should have been equal to G. Question for you guys. What's the probability you'll need under 100 attempts to mine 2 Bitcoins? I'm going to give you a whole whopping 2 minutes to think about this. Don't try and give me the number, but try and do the process. Define the random variable. Tell me what the question's asking in terms of that random variable, and then we'll just think what equation do we want to use. Okay, go for it. Okay. I want your guys' answer to start with these 3 words. You can choose Y if you don't like X, but I want to start with let X be. And then I want to define something that the problem's asking about. And it's asking, 100 attempts to mine 2 Bitcoins. I want X to be some number that question is referring to. Anyone who hasn't said anything, they're like, I want to share. I want to tell the world. Yes?
X be the number of Bitcoins behind the first 99 attempts.
What is probably you need under? Oh, that would definitely solve it. Oh my gosh, that's such a good way. Okay, X be the number of Bitcoins mined. In the first, did you say 100? What was your?
100 or 99 attempts.
Okay. 99, number of Bitcoins mined in the first 99 steps. This is interesting. Okay, and then what's the question asking? Like, now let's write the probability question. Like, is this asking the probability that X is the number of Bitcoins mined in the first 99 steps? Is it probably that it's asking the probability that X equals?
X is greater than or equal to 2.
Greater than or equal to 2. Okay, so you guys, let's think about this for a second. X is a good answer, slightly different than how I approach it, but I think you might actually get to the same answer. Let's double check. Let X be the number of Bitcoins that you mined in your first 99 steps. So you're saying I'm going to flip, why not 100?
Does it need under 100 steps?
Under 100, okay. So I'm going to flip 99 coins. Every coin has a probability of coming up heads, that we've got PA, and you can say what's the probability that X is greater or equal to. So then you say X is a binomial, let N equals 99, and P equals PA. Probably that X is greater than 2.
Chris, is the question saying mine exactly 2 Bitcoins or 2 or more?
Exactly 2 Bitcoins.
Then should be X is equal to 2 then?
But if you mine more than 2 Bitcoins in 99 attempts, then that means you'll get to 2 Bitcoins before the 100th attempt.
And I think I buy that. So I agree that has to be greater than, because you could get more than 2 Bitcoins and you want to count that. I buy that works. It's a different way than I thought about it, but I actually do think this will get to the same answer. Did somebody have a different approach for this? Did you have a different random variable declared? Yes?
X is the number of attempts until you get to mine 2.
Until 2 Bitcoins. Okay, then what's the problem asking? It's asking the probability that X
is less than 100.
That X is less than 100. Okay, and then finally, what is X? The big reveal.
It's a negative.
It is a negative.
Where R is 2 successes.
Okay, where R equals 2. And what does P equal?
I think it's 1/2.
It's 1/2 to the power G. It's the thing we defined in problem A. This is how I approached it. And then you can use, probably that X is less than 100, you can just use the negative binomial equation. And I think this also answers the question of why negative binomial gets its name, because I do think that is this relationship that people are referring to in the name. But I think these are 2 different solutions, to the 2 different good solutions to this problem. Yes?
Why does the summation start at I equals 0? Wouldn't that be like 0 attempts?
Yeah, okay. And And this should say 2 Bitcoins. So I've typed out there. So let's talk about this. Your question is number of attempts until you get to 2 Bitcoins. X can't be 0. Good point. Also, X can't be 1. You can't have 1 trial. Technically, this is a more elegant solution. But technically, the probability of 0 is 0, and the probability of 1 is 0. So you'd just be adding 2 zeros to this, which would get you the same number. But I think this is a much more elegant way of writing it. Good, good, good. Show some insight. Yes?
Why can't it be 1? Like, why are 0 and 1 both impossible?
Because it's the number of tries until you get 2 Bitcoins. If you pull it once and you get 2 Bitcoins, like, what a time to be alive. Just like retire from Stanford, enjoy your new yacht. Okay.
Why is why does the sum go up to 100 instead of 99?
Typo, man, it's sloppiness. They let you become a professor even if you get off by ones. Okay, and certainly I really appreciate it. So 2 different approaches, totally fine, and 2 very good ways of seeing a problem and recognizing the math behind it.
For the expanded answer for the binomial, would it just be the sum of that after, like, when x is greater than or equal to 2?
That's such a good question. How would I actually do the next step here? I wouldn't do the probability of 2 plus 3 plus 4 plus 5 because that feels onerous. I would do 1 minus the probability that x equals 0 plus the probability that x equals 1. And this is the probability that x is greater than or equal to 2. So these are the only 2 cases that don't count. And this seems like less work to do. But good question. Okay. I was going to give a pedagogical pause. This is your chance to like summarize what we learned about. We have long lectures. I want you guys to have a break. So take a moment. If you guys have questions, please do ask me. Otherwise, try and summarize. We've talked about 4 random variables at this point. Try and see if you can get your head around what they all mean. Okay, yeah. Okay. Do you guys like the pedagogical pause? Do you guys like having a moment just to relax in the middle of lecture? Yeah. You're not? Okay. Man, they're long lectures. There's just so much probability to know. We get to have a wonderful conversation right now. We are at a beautiful point where I really think I could give you any discrete random variable and you could run with it. You could probably read it, use this probably mass function, and start to solve problems. And you could really quickly go from knowing 4 discrete random variables to knowing hundreds. You have the ability to learn new ones. That's what really matters. But you are missing something. And it's that not everything in our world is discrete. So if you're working on problem set 2, for example, one of the things that you're doing is you do this estimating the location of a phone based on the distance to a cell phone tower. I think that's the very last problem. But that assumes that you can take a 2-dimensional world and discretize it and think about all the locations as being discrete squares. But we know that the real world is not discrete. It's in fact continuous. And it'd be great if we could start to think about this continuous space. And the simplest example I can give you of the world not being discrete is this very humble Python function called random. And it exists in every language. Random, the base of a lot of random number generators, is a continuous number between 0 and 1. If you call random, you might get 0.11, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But there's a reason that this is so hard to reason about. In these random variables, like consider a binomial, you can ask what's the probability of getting a 1 back? You can ask what's the probability of getting a 2 back? But let's see if we can call random. So I think math.random, and I will make this much bigger. You know, if you were generating something with coin flips and you talked about number of trials, you could ask the question, what's the probability that this would return us back a 2 if it's simulating the coin flips? If this was simulating coin flips, you could ask, what's the probability to give us back a 3? Oh, it's random. Random.random, forgive me. The problem when we get to the continuous world is this is certainly a random variable. It's going to take on a value, and it's going to take on a value with different probabilities. But it's hard to reason about. What's the chance of getting exactly this number? And especially if you allow this number to keep going to infinite precision, it becomes so painful to think, what's the probability of getting exactly this number? So even though continuous is, at the end of the day, not going to be too hard, there's this one itch we have to scratch. So let me give you another version of that same story. Let's say the average rate of earthquakes is 1 every 100 years. Using a Poisson, we already have the language to talk about the probability of different numbers of earthquakes in a year. You can say, what's the probability of 2 earthquakes in a year? You can talk about the probability of 3 earthquakes in a year. But our language breaks down when we start to talk about how long until the next earthquake. Like if you ask the question, what's the probability that it's 4 days until the next earthquake? This really awful bug shows up. When you say 4 days, do you mean 4.000000000000000000000 days? And if the earthquake shows up 1/billionth of a second later, that doesn't count as being 4 days? Time, when you think about amount of time until an event, is continuous, and it gets so hard to think about a probability mass function in the continuous space. Now, riding the bus is a fun thing. I thought this would be a fun little ride to bring us from the discrete to the continuous world and to really illuminate what I'm talking about. We've thought about this problem while waiting for the Marguerite. Imagine you're running to the bus stop and you don't know when the next bus arrives. You have a distribution of probabilities for when the bus shows up. You show up at 2:20. What's the probability that you wait less than 5 minutes? So, I think you arrive at 2 o'clock. Yeah, 2:15. You arrive at 2:15. And you want to know what's the probability you wait less than 5 minutes. Forgive me. So if you arrive at 2:15, how do you think about the probability that the bus arrives at 2:17 and like infinite precision seconds? It gets so hard to think about. But here's a hackier thing we could do. Imagine this is 2 o'clock, and this is 2:05, and this is 2:10, and everything here is a 5-minute chunk. If you could represent time not as a continuous, but time is broken up into 5-minute chunks, then this problem becomes a lot easier to think about. This is the probability that the bus shows up between 2 and 2:05, 2:05 and 2:10, 2:10 and 2:15. If you show up at 2:15, the chance that you wait for less than 5 minutes is just going to be the probability that the bus shows up in this 5-minute section. Does that sound good? But time isn't broken up into 5-minute sections, is it? Can we break it up a little bit more and start to reason about this probability if we made time a little bit more fine-grained? Okay, let's break it up into time being 2.5-minute sections. If you break time into 2.5-minute sections, your belief of when the bus will show up, it gets a little bit smoother, and the width of every single belief becomes a little bit less because this here is representing, between 15 minutes and 17.5 minutes, and this is representing 17.5 and 20. This is discrete. This is a sort of probability that we can absolutely reason about. Seems totally fine. If you want to know the probability you wait 5 minutes, you just add the probability that the bus shows up in this 2.5 minutes to the probability the bus shows up in this 2.5 minutes. Those of you guys who are fans of calculus might see where I'm going this. Like really, to be honest with time, we shouldn't allow time to be 2.5-minute sections. We should make it smaller. And then we should make it smaller. And we should keep making our intervals of time smaller and smaller and smaller until they're infinitely small. And if you did this, you would basically have invented calculus again. And you'd be particularly inventing this idea of integrals and area under the curve. Your buckets become smaller and smaller and smaller, and your question no longer becomes the sum of the values of each of those buckets, but rather it becomes the integral under this new curve that you've gotten as your buckets became infinitely small. This area is called the integral, and this new curve that you got when time became infinitely small is no longer a measure of probability, but it's the derivative of probability. And those words strike fear in some people's hearts, but for other people, you're like, oh, what a happy place. It's going to be a happy place for all of us. So as probability, as our interval got smaller and smaller and smaller, eventually you no longer have a probability. You have how much is the probability changing when I take an infinitely small step in my x-axis. This leads to the most critical idea you need to understand to get continuous random variables. And once you understand this idea, the rest will come quite naturally. But this is going to take a second to get used to. When we talk about a continuous random variable, like this one, for example, that can take on values with infinite precisions, we can no longer ask the probability that the random variable takes on a precise number. Instead, we represent our probability mass function using this other thing called a probability density function. The probability density function is the derivative. And if you want to find a probability query, you're not just going to be looking up from a probability mass function. Instead, you're going to be integrating under a probability density. Wow. And it's going to be just fine. I want to just go over notation really quickly. This probability density, this derivative, is the thing that's the most important thing to know for a continuous random variable, just like the PMF is the most important thing to know for a discrete random variable. Okay. Integrals, you're going to have to do them, but they're loving, not scary. And here's one of the ways I talk about integrals in CS109. You really need to know the concept of integral. You need to know when you need an integral. There is wonderful calculators out there who can do the integrals for you. You don't need to memorize all the integral equations. You just need to get the concepts. You have to get the concepts of a derivative and the concept of an integral. That's what it looks like to be a modern mathematician. Integrals allow you to take a curve and answer the question, what's the area under the curve? So if this is your curve, then an integral under that curve between a and b will be written with that notation, and it will represent what is the area under this curve. If this is the integral, then this line is the derivative of that same integral. Okay. So if you ask, the value of this line would be, what is the rate of change of my area at exactly that point? If this is a review for you, I would recommend just go watch a Khan Academy video on integrals, and you'll find it, just to understand what an integral is, because you really want to understand what integral is coming into CS109. So back to this question, my claim is, if you really could represent a belief distribution about when the bus shows up, the best representation would be this derivative of probabilities that we call a probability density function. And if somebody gave you that to answer this probability question, we would just be finding the area under the curve between the values 15 and 20. This is a little abstract, so we're going to make it a little bit more concrete by learning about two useful random variable types. Couple things to note to give us some intuition. If you take a probability density function and you integrate between 2 points, you're asking the question, what's the probability that this random variable takes on a value between a and b? And since that's a probability, it should be a number between 0 and 1. Also, if you say, this is the derivative of the chance that this continuous random variable takes on a value, and you integrate from all the possible signs from negative infinity to infinity, that's like, what's the chance that the bus shows up between negative infinity seconds and positive infinity seconds? You're like, 1, I guess assuming that the bus ever shows up, which maybe it won't. But assuming that you're just talking about time until something happens, it will be 1. So this is a question that I want you guys to all have baked in. I'm going to ask it to you one other time in this class. And when I ask you, what do you get when you integrate over a probability density function, I want you guys to just yell out this, a probability. Can we try it out? What do you get when you integrate over a probability density function? Oh, fantastic. Okay, so the probability density function isn't a probability itself. It's something that you can use to calculate a probability. Probability density functions, they're how probability is changing at a certain point in time. It's the derivative. So if it's flat, that means the probability is just increasing the same amount of time as you increase more area into your query. If it goes up versus it goes down, which of these three do you think represents the belief that a bus is more likely to arrive close to 3 p.m.? So this is 2 on the left-hand side, and this is 3 p.m. on the right-hand side. So this is 2 p.m., 3 p.m., 2 p.m., 3 p.m. Which of these says the bus is more likely to show up at 3 p.m.? I like shouting. We're just going to do a little bit more shouting. Can we all just shout? A, yeah. In this one, it says, a probability density is relative likelihood because the derivative tells you how much you'd be contributing to an area. Here, the derivative is high over there and low over here, and that means that this is relatively a more likely space. This means any time is equally likely. The bus could just as well show up at 0 minutes as 60 minutes, And this is a different distribution that says it's not equally likely. It's way more likely to show up at, say, like 10 minutes and less likely to show up at other points in time. So the main takeaway from this slide is that probability density function, it's not a probability. You'd have to integrate under it to get a probability, but it is a relative expression of belief. It does turn out that if you compare probability densities, it's meaningful, and I will formalize that for you on Monday, but I just want to point that out now. Okay. Probability density is not a probability. Rather, it is the derivative of probability, and therefore it has units of probability divided by units of x. In our case, this was time. So if you look at the probability density at a certain point, you might get that it's 0.05, and that would be like, the units would be probability per minute. It's not a probability itself. You'd have to integrate it to get probabilities. One cheapo way to integrate is you just look up a value and you times by a width, you get a rectangle. And if you get a nice approximating rectangle, then it's a fine approximation of your integral. So if you look up one of these values, multiply it by a width of, say, 2 minutes, then you would get something that looks like an area under the curve and something that looks like a good approximation of a probability. Oh, here is a wild thing which is totally possible. Here is a probability density function for when the bus shows up. What am I claiming here? I'm claiming I am positive the bus is going to show up in this 30-second window. It's not showing up here. It's not showing up here. All of the probability area under the curve shows up in this 0.5 minutes. But as I mentioned, f of x is not a probability. It's rather the derivative of probability. And I wanted to point out that that means that f of x can be a value greater than 1. Are probabilities ever greater than 1? No. Are probability derivatives ever greater than 1? Yeah, it's totally possible, especially if like the width here is less than 1. That would allow the height to be something greater than 1. Anyways, another major takeaway is just that this probability density, it's not a probability, it's the derivative of probability. At this point, I hope you guys are feeling more comfortable with a probability mass function. It's the most important thing to know about a discrete random variable. It relates values that your discrete random variable could take on with the probability that it takes on a value. The analogous idea for a continuous random variable is not a probability mass function, it's a probability density function. And it is the derivative of how probability is changing at a particular assignment. Because it's not a probability, we use this little f to represent this probability density. And it's the most important thing to know about continuous random variable. This is like complete information about your discrete random variable, and this is complete information about your continuous random variable. But they're both the representation of the relationship between values the random variable could take on and how likely it is to take on those values. Okay, and you can read a little bit more about this definition. I'm going to give you a problem. It's actually a really cool physics problem, but I'm just going to give it to you as a straight continuous random variable. X is a continuous random variable, and I'm going to give you the probability density function. The probability density function for this continuous random variable has this beautiful equation, which if you graphed it out, looks like a semicircle. I'm also going to run a simulation where I get 100,000 samples of x, and I'm going to show you the histogram. My question is, how would you take this information and calculate the probability x is greater than 0? And let me give you 3 ideas, and hopefully this builds some intuition. The first idea, the one that I've been kind of hammering, is that this is complete information because you can always integrate under it to get a probability. So my first solution is you can say the probability that x is greater than 0 is the area under the curve of the probability density function from 0 until infinity. But since it can't take on values greater than 100, it'll be the integral from 0 to 100. So you could just integrate this whole puppy, and you'd be like, I'm going to integrate you from 0 to 100. Don't forget your dx over here. And that's not wrong. But while that is one approach, I want to show you simultaneous approaches that maybe will give you some insight. You could also look at all of my samples and you say, how often were my samples greater than 0? And if you did that, instead of getting an integral from 0 to 100, you get a sum from 0 to 100 of my histogram. That'll be an approximation. It won't be as correct, but it'll give you a number that's just about right. And this is just for humor. A third one is you can no semicircles, realize that this is defining a semicircle and knowing that the area on the right-hand side has to be equal to the area on the left-hand side. And you're just like, well, probably x is greater than 0 is 1/2. This is just supposed to be a toy problem to get practice with probability density functions. If you guys are curious where this comes from, it comes from quantum physics. And there they consider random matrices. And then every element in the random matrix is like background noise. And they want to know what's the probability that if you chose an eigenvalue of that matrix that would be greater than 0. Turns out that whole thing got rephrased to the random variable problem that we just solved. But that's not that important right now. I just thought it would be fun to share. OK, what do you get if you integrate over a probability density function? You guys got it. That's awesome. OK, so now we have to learn 2 new random variables, the uniform, and then we're going to learn the exponential. The uniform is the probability random variable for a number which is equally likely to take on value between a lower bound and an upper bound. So it has 2 parameters, alpha and beta. Alpha is the smallest value you can take on. Beta is the largest value it can take on. That random I showed you over here, it's a uniform. The lowest value you can take on is 0, and the highest value you can take on is 0. The most important thing to know about a continuous random variable is its probability density function, which you can use to solve probability questions. And it says, how relatively likely is your random variable to take on some value little x? And for the uniform, it's constant. It's 1 divided by the size of the range, so the max minus the min. In the case of the random I showed you, this is just going to be 1 divided by 1 minus 0. So it's saying the probability density is 1 in all locations, and it's 0 otherwise. If you had to graph this out, it would look like a flat line, where below alpha, you can't get anything. Above beta, you can't get anything, and it's equally likely in between that area. A couple properties. You can know the expectation if you have a uniform. You can know the variance. So if you ask what's the variance of these numbers you got right here, then I would just do 1 minus 0, so that's 1 squared divided by 12. The variance of these numbers is 1/12. Now you know. OK. So if this is my bus and my belief about when the bus shows up is uniform in the range 0 to 30, then what is the probability to wait less than 5 minutes? Well, I'm going to integrate from 15 to 20, that's my 5 range I care about, over the probability density function. The probability density function is just going to be 1 divided by 30 minus 0. When I integrate, this constant just becomes an x. If you looked in Wolfram Alpha, you're like, what's this integral? It would just give you that it's x divided by that constant. And then I evaluate in the range 20 to 15, and when you do that, you get 5 over 30, which makes so much sense. If it's equally likely at all points and you wait for 5 minutes, and it's equally likely to show up at any time within 30 minutes, then your probability of it showing up in those 5 minutes is 5 over 30. Yes?
Kind of a tangential question, but the binomial graph that we used to have, is that also a probability density function?
It is not. It's a probability mass function. So the question is this also a probability density function? It's not, because it's actual probabilities. And probability density functions, they're going to look like this. Ooh. Where they're derivatives probabilities. And notice how there's no gaps. You know, we're going to define the derivative probability at every single point. Whereas on probability mass function, there should be gaps. It should be more like a bar chart.
But if you want to find the probability of something being less than 5, then also you kind of add up the probabilities.
OK, I'm with you. So you're saying like you still do something similar to an integral. If you want to know the probability less than 5, you would add this to this to this to this to this to this. It's kind of like you're doing an integral, and that's the deep parallel. Yeah, if you're doing the probability that the discrete random variable is in a range, you're adding. If you do the probability continuous random variable range, you're doing the continuous equivalent of adding, which is integration. Yes?
So for a continuous distribution, is the probability mass function is the integral probability distribution function?
There's no probability mass function.
Like, can you not? That's not allowed.
It's not allowed. No one. It's like off limits. No probability mass functions are the thing of the past. It's from our discrete world. In the continuous world, only probability density functions. Good question. OK, I want to introduce you to one final random variable before we call this a day. And it's the last one. Look at what a day we have had. We're going to be learning about the exponential. The exponential is the continuous friend of the Poisson. I think of them as best friends. I think they grew up together. They had such a good time together. They're so similar in so many ways, but they've got their own personalities. So we're going to be thinking about an experiment that lasts a certain duration until you get a success. An exponential random variable is going to be the time until a success. And When you talk about the time until you get a success, if you declare it to be an exponential, you would write it like this. You say, the time until my success is distributed as an exponential, and it takes a parameter lambda. Why does it take a parameter lambda? That reminds me of the Poisson. Poisson was, the number of events in a fixed time frame when there's a Poisson process. Exponential is also during that Poisson process. It's like those Uber drivers are showing up, or those requests are showing up, and this is the number of time until the next request shows up. So if the Poisson says, you have fixed time, how many events are you going to get in that fixed time? The exponential says, how long until your first event? So, if you declare something to be an exponential, for example, you have time until your next earthquake, or time for a request to reach your web server, or time until the end of a cell phone contract. Time until is the key word for an exponential. Poisson was number of events in time, and exponential is time until. They're very good friends. The probability density function is given by this beautiful equation, lambda times e to the power of negative lambda x. Lambda is the average number of events within 1 unit of time. And if you were to draw it out, it has this curve which exponentially decays, and there's where its name exponential comes from. I'm going to give you the expectation, and I'm going to give you the variance. So as long as you can recognize something as an exponential, you inherit all 3 of these things for free. You're like, I like free stuff. Awesome. Let's try this out. At the beginning of class, I said, follow along, and we'll be able to answer the question, what's the chance that it'll be 4 years until the next big earthquake at Stanford? Here's the information I'm going to give you. I'm going to give you lambda. It's the same lambda as a Poisson. That's the average number of earthquakes per year. The average number of earthquakes per year in California is 0.002. So 0.002 earthquakes per year, and that's your average rate. What's the probability of 0 major earthquakes in the next year? You could solve this using a Poisson because of the 0. What's the probability of 0, or that it takes a whole year until the next earthquake? But this you can also express as an exponential. And I would challenge you to try and express this as an exponential. Think about it. I'm going to clear up the board, though we're going to just look at the answer in a second. Okay, if you wanted to make this an exponential, you would say, this is the Poisson version. You could say x is the number of major earthquakes next year. You define it as a Poisson. You say, what's the probability that x is 0? You could use your probability mass function. What if I ask, what's the probability of a major earthquake in the next 30 years? Now, you could set up a different Poisson, which is the number of earthquakes in 30 years, or you could approach it as exponential. A lot of times, you'll have a choice between exponential and Poisson, but a lot of problems naturally lend themselves to exponential better. My question is, what are the random variables here? So probability of a major earthquake in the next 30 years. Instead of talking about number of earthquakes in 30 years, I'm going to let y be years until the next earthquake. Now, the question is just asking what's the probability that x is less than 30. But because I defined it as how much time until the next event, now y is an account of events, instead y is time. And in this case, it perfectly fits the story of an exponential, which is the time until an event. So the time until event I'm declaring as an exponential. You have to give the rate of events per unit time. And then you immediately inherit that the probability density is equal to that beautiful equation. You could substitute in lambda, in which case the probability density function would be this beautiful equation. And there's an e missing here, though. Now, what's the probability that y is less than 30? That's all we have to do. And up till now, these questions have been just plug and chug. But for a hot moment, this won't be just plug and chug. Because is the probability density function a probability? It's a derivative of probability. If you wanted this one, we have to solve this integral. It's the integral in the range of the values we care about over the probability density function. That gives you the probability that y will be in the range 0 to 30. Let's go there. Whew. Okay, you need to know this integral review. You need to go integral of e to the power of cs is equal to 1 over c e to the power of cx. E is such a beautiful thing to integrate. In which case, when you took this integral, you would get lambda times 1 over lambda e to the negative lambda. And you would evaluate this in the range 30 to 0. Once you have the integral, you just plug in 30 into this number, subtract off plugging 0 into this number, and you would get 0.06. Who looks forward to doing an integral every time you have to do a continuous random variable problem? Will was like, yes, awesome. Okay. I just want to show you one other question, and then I'm going to show you a beautiful thing about exponentials that will make you tear up. It's so beautiful. Why is the number of years until an earthquake? What if I change my question to the expected number of years until the next earthquake? So now I have the same y. It's still an exponential, but I'm no longer asking what's the probability that you get an earthquake in the next 30 years. Instead, I'm asking what's the expected number of years, in which case you would just use the expectation of this new random variable. You'd just plug in that formula. If I asked you the variance of years until the next earthquake, you would just use the variance formula. Okay, standard deviation. Yeah, exactly. You just say, here's my exponential, and I want the variance. I get that. And then standard deviation is just going to be the square root. I'm just looking up this formula. Like, why do I know that this is the formula? That's because if you look at your exponential, that is the formula for the variance of an exponential. Now, I want to leave you guys with hope. So I want to talk about how you can solve these problems without integrals. I'd like to introduce you to a great new friend who you can bring on your wonderful probability journey with you. Welcome, everybody, to the cumulative density function. It's not a probability density, it's a cumulative density. And it's not written in PDF, it's written as a CDF. And it's a special thing. The CDF, which we write as a capital F, represents the probability the random variable is less than the input to the CDF. So this is a function. If you put in a 0.5 to this function, it will return you what the probability that your random variable is less than 0.5. So it's a function. That's where the f comes from. And if you learn how to use a CDF, you may never need to do an integral. You may need to know what an integral is, but you might not need to use it. It has this shorthand. I will often try and just write it using the normal notation. Okay, it's a function. You put in values, and it gives you back probabilities, particularly the probability that your random variable is less than that value. Here's the CDF of an exponential. So it's got this nice closed form equation. You could have derived it. You could say, I want to derive the probability that x is less than little x. You could start with the integral of your PDF, plug and chug, and when you're done, you'll have derived that the probability that x takes on a value less than little x is this number. But how could you use that? Let's try answering a few questions using both the PDF and the CDF. So this is a plot of the CDF of my exponential, and this is a plot of the PDF. Sorry, it looks like there's a little. Slideshow decided to give me a little bit of excitement for a second there. What if you want to ask the probability that x is less than 2? There's two ways of solving it. You can solve it using the PDF, and you can solve it using the CDF. If you wanted to solve it using the PDF, you'll do the thing that we've said like 100 times in this lecture. You would take the integral from 0 up to 2 under this curve. You would use an integral. But can you solve this just using the CDF? Recall that the CDF is defined to be the probability that x is less than whatever your input was. What would you put as an input? Just yell at me. Yell at me confidently. Yeah, it's 2. If you just put a 2 into the PDF, you look up this value, and it directly answers your question. If you just put a 2 into the formula for the PDF of an exponential, you would just have to put in lambda and your 2, and you would get a number. And you would get the same number regardless of how you solved it. Now, obviously, it's good for answering questions when the form probably x is less than something, but what if probably is greater than 1? Again, using the PDF, we can calculate the integral. Calculate the integral from 1 to infinity under that curve. Go. Or is there a way that we can use this beautiful friend, the CDF, to solve this problem? 1 minus. Yeah, if you just look up the value at 1, it will give you the probability that x is less than 1. If you want the probability that x is greater than 1, you just do 1 minus that value. You're done. And you didn't have to do an integral. Like, look at this. You're laughing. You're having a good time. The person who's doing this tears. The person using the PDF tears all the way, and the person who uses CDF just having a blast. But then the PDF has their revenge, because obviously this question is easier to solve with a PDF. The new question is, what's the probability of the random variables between 1 and 2? And here the PDF just like, I'm going to integrate like I always do. What does the CDF do? An idea?
Subtract.
Subtraction, woohoo! You look up the value at 2 and you look up the value at 1. The value at 2 is the probability that x is less than 2, and the value at 1 is the probability that x is less than 1. If you take the probability that it's less than 2 and subtract off the probability that's less than 1, it's like you're taking this integral and you're subtracting off this bit, which just leaves you with the purple bit in the middle. CDF can solve all of these probability questions, which leads me to the final question of today. What's the probability of a major earthquake in the next 4 years? Well, it's an exponential, but I'm going to use a CDF. I'm just going to ask, what's the probability that's less than 4? It's a CDF of 4. I'm just going to plug in this nice little equation, and you get that there's a 0.008 probability of a major earthquake in California in the next 4 years. I'm feeling lucky. I hope you guys are too. That's the end of today's class. Have a fantastic week. If you have more questions, come ask me afterwards, and see you guys back in class on Monday.